Today, we're diving into something really fascinating from physics.
Yeah.
It's all about how we track particles, the ones producing these incredibly high-energy collisions.
Right, like inside those huge particle accelerators people hear about.
Exactly.
And our mission, yeah. Looking at the source material you provided, which is a pretty detailed analysis, really focused on the physics basics, is to understand why. Why do charged particles curve like that when they fly through the magnetic fields and detectors?
And maybe more importantly.
And what do physicists actually get from watching those curves? What does it tell them?
Right. So get ready. We're going to unpack this kind of mysterious dance of subatomic particles, all guided by magnetic forces. Let's do this deep dive.
Okay, so let's picture it. You've got particles smashing together, yeah, nearly the speed of light. Think like the Large Hadron Collider at CERN.
Okay. Big smash.
Big smash. And right there, at that tiny point, they call it the collision vertex. Boom. You get this spray of brand new particles flying out.
And many of those are charged, electrically charged. Things like electrons, protons, muons, pions.
Exactly. And that charged part, that's absolutely critical here. Your source material jumps right on this.
Because the neutral ones, photons, neutrons, they're going to act completely differently inside the detector, aren't they?
Totally differently. And it all comes down to the magnetic field. The detector isn't just, an empty box. It's filled with really powerful magnetic fields put there on purpose.
And the source points out, this field is usually set up perpendicular, right, to the direction the original particles were coming from.
Yeah, that's not just by chance. It's a very deliberate setup.
Why?
Because that specific orientation, well, it makes the key physics principle work perfectly. The Lorentz force. That's what bends the paths.
Oh, the Lorentz force, okay.
And what your source material really digs into is how this force becomes like the physicist's #1 tool here. So the Lorentz force, it's just the force a charged particle feels when it moves through a magnetic field. The key thing, and why it's so important for tracking, is that the force always acts perpendicular.
Perpendicular.
Yeah, perpendicular to both the way the particle's moving and the direction of the magnetic field itself.
Huh. Okay, a force that's always sideways to the path. That feels a bit weird. What does that actually do to the particle?
Well, that's the clever bit, as the source highlights. A force that's always perpendicular to the motion. It doesn't do any work on the particle.
No work, meaning?
It doesn't speed it up. It doesn't slow it down.
Wow.
Its only job is to change the direction the particle's going.
Okay, right. It just steers it,
Yeah.
bends the path, but the speed, the energy stays the same. Like trying to turn a car by pushing sideways on the door, not from the front or back.
Exactly like that. And think about it. A force that's always perpendicular to the velocity, constantly tugging the particle away from a straight line, pulling it towards some central point.
That sounds like circular motion.
A centripetal force, that's exactly what it is. It is the centripetal force in this situation.
So in a nice uniform magnetic field, if a charged particle is moving perpendicular to the field lines, it's forced into a circle.
Precisely. Now, if the particle has some velocity component along the field lines too, it doesn't just go in a circle, it makes a spiral.
Like a corkscrew.
Yeah, a helix. But even then, if you look at the shadow, the projection of that path onto a flat plane perpendicular to the field, that projection is still a circle.
And that curve, that circle or projected circle, is what the physicists are actually measuring in the detector.
That's the one. That's the track curvature.
Okay. So magnetic field plus moving charge gives you a Lorentz force. Lorentz force acts sideways, makes the path curve. Got it. But what does measuring the curve tell us? What's the payoff?
Right. This is where the source gets really specific. That radius, the size of the circle or the helix, it's packed with information.
How so?
There's a fundamental relationship, pretty straightforward actually. The radius of curvature is directly proportional to the particle's momentum.
Okay, more momentum, bigger radius. Makes sense. Harder to turn.
Exactly. And it's inversely proportional to the particle's charge magnitude, Q, and the magnetic field strength, B. So the formula is basically R equals P divided by Q times B.
Whoa, hang on. So if you know B, the magnetic field strength, which you do, right? You built the detector, you mapped the field carefully.
Oh, yeah, absolutely. Very precisely known.
And you can measure R, the radius of that curve from the track.
Yep, using sophisticated tracking detectors.
Then you can just calculate P, the particle's momentum.
Yeah.
Just like that. That seems really powerful.
It is. It's absolutely fundamental. Particles with high momentum, like you said, they resist bending. They make these wide, large radius curves. Low momentum particles, they get whipped around easily. Tighter curves, smaller radius. Measuring that curvature is like the primary method physicists use to figure out the momentum of charged particles flying out of the collision.
Wow. And the source also mentioned the direction of the curve,
Right.
clockwise versus counterclockwise.
Yes,
Yeah.
that tells you the sign of the charge.
Positive or negative.
Exactly. You know the magnetic field direction. You see which way the track bends. You use basically a version of the right-hand rule you might remember from physics class.
Vaguely.
And that tells you if it's a positive charge, like a proton, or a positron, or a negative charge, like an electron, or an antiproton. Particle or antiparticle.
So just from looking at how a track curves out from that collision point, how tight the curve is, and which way it bends, you immediately get its momentum and its charge sign. Two critical pieces of info right off the bat.
Right off the bat. And this is why, the source material really emphasizes track reconstruction. It's not just about looking at pretty pictures, although they are kind of cool.
They are pretty cool.
Physicists are doing really complex geometrical fits to these tracks, measuring the radius and direction super precisely for every single track spraying out from the vertex. That data, momentum, and charge, it's the first big step in figuring out what particle you're actually looking at. Narrows down the options massively.
Yeah, because different particles, even with the same charge, have different masses, right? So for the same energy, they'd have different momenta, maybe leave different kinds of tracks.
Exactly. Or sometimes particles don't live long enough to reach the outer detectors. They decay. So you track their decay products, measure their momentum and charge from their curved tracks, and then you trace those tracks back. If they meet up at a point away from the main collision.
A secondary vertex.
A decay vertex, yeah.
Yeah.
That tells you something decayed there, and the properties you measured for the decay products help you figure out what the original parent particle was. It's like doing forensics with particle tracks.
Okay, but what about tracks that aren't just perfect arcs? Sometimes in those pictures, you see them kind of spiral inwards, getting tighter.
Yeah, that's another clue. That tells you the particle is losing energy as it travels.
How's it losing energy?
Well, as the charged particle plows through the detector material, there's gas in some tracking chambers, layers of silicon. Eventually, the calorimeter is designed to stop them and measure their total energy.
Right, it's not empty space.
Not at all. It's interacting with the atoms in that material. It bumps into them, essentially knocking electrons off. That process is called ionization.
And knocking electrons off takes energy.
It costs energy, yeah. So the particle is constantly losing a bit of its energy and therefore its momentum as it flies outwards.
Okay, so momentum P is going down.
And look back at that radius formula. R equals P QB. If P is decreasing and the charge Q and field B are constant,
Then R, the radius, must also get smaller.
continuously smaller, which means the circular path tightens up. It spirals inwards.
So a spiraling track is a sign of energy loss.
Exactly. It tells physicists the particle is losing energy and how fast the spiral tightens, the rate of energy loss. That gives even more information about how the particle interacts with matter. That helps identify what kind of particle it is. An electron loses energy differently than, say, a heavier muon.
That's fascinating. So much information packed into just the shape of the path.
Okay.
So we've got curves and spirals for charged particles. But you mentioned neutral particles way back at the start. How do they fit in? Do they just not show up in the tracker?
Well, they show up by not showing up, in a way. Think about the Lorentz force again, F equal QVB, essentially.
Right.
For a neutral particle, the charge Q is
0.
0, and anything times 0 is
0.
Right. So the Lorentz force on a neutral particle in the magnetic field is 0. Nothing. Nada.
The magnetic field doesn't affect it at all.
Not one bit. So what does it do?
Keeps going straight.
Keeps going straight in a perfectly straight line from the collision vertex
Until
it either hits something else deeper in the detector, like the calorimeter is designed to absorb particles and measure energy, or maybe just flies right out the detector without interacting much at all, like a neutrino often does.
So if physicists see energy deposited way out in the calorimeter, but no curved track leading to it from the vertex,
they infer a neutral particle traveled that straight path. Or sometimes they add up all the momentum they do see in the charged tracks, compare it to what they expect from the initial collision energy, and if there's momentum missing in a certain direction.
that points to unseen neutral particles carrying it away.
Precisely. So the absence of a curved track is just as informative in its own way.
Okay, that really pulls it together.
Yeah.
The magnetic field is like the primary sorting mechanism, isn't it? separating the charged from the neutral, and then bending the charged ones in ways that reveal their secrets.
Absolutely. The whole tracking system, it's fundamentally built around exploiting this basic interaction, the Lorentz force.
Okay, so let's just recap this then. These beautiful curved tracks you see spilling out from collisions in those detector images, they're not just random patterns.
Not at all. They're the direct physical consequence of the Lorentz force. It's that force bending the paths of charged particles as they speed through those carefully designed magnetic fields inside the detector.
And as the source material really drove home, by measuring the details, how much they curve, which way they curve, whether they spiral.
Physicists can pull out crucial properties,
Yeah.
things like momentum and the sign of the charge. And that's absolutely essential for the first step, identifying the particles, figuring out what was actually created in that smash-up and how the whole event unfolded.
So knowing this helps you understand how these giant experiments manage to see this invisible subatomic world, right? How they learn about matter by smashing it apart and watching the pieces fly, turning these tiny little arcs into fundamental knowledge about the particles.
Yeah, it's pretty amazing when you think about it. And maybe here's something to chew on.
Okay.
We've talked about how measuring the main curve tells us momentum, but what if there are even tinier deviations? Subtler patterns in those tracks, maybe like little wobbles or unexpected kinks, things that aren't predicted by just the simple Lorentz force and energy loss.
Like imperfections in the curve.
Yeah, what might those reveal? Could they be hints of particles we haven't even discovered yet? Or maybe signs of forces or interactions that aren't in our standard model of physics? Just imagine the level of precision you'd need to spot something like that. And the calculations involved. It makes you wonder what new physics might still be hiding, almost invisibly, within the exact shape of those tracks.